Expansion of solids. Solids expands on heating, but their expansion is less compared to liquids and gases. So if you observe, the solids, liquids, gases all will expand. Solids will expand when you heat, liquid will expand, gases also will expand when you heat. But among all, the expansion is less for solids compared to liquids and gases. Compared to liquids and gases, expansion is less for solids. So here what we are going to discuss here means whenever some substance is heated, they will expand. So the expansion is there not only for solids, for liquids also will expand, and also gases also will expand. When heated, liquids expand, gas expand, solids will expand. Fine, all are expansions, and everywhere we found expansions. Liquids expand, gases also will expand. But among all, compared to liquids and gases, what happen? Solids expansion is less. Expansion of solids is less. Why means in solids the molecules and atoms are closely packed. In atoms and molecules are closely packed in solids. So compared to liquids, gases are very free to move like that. So among solids and liquids, if you observe, solids, the molecules and atoms are very much closely packed, so that we can say that expansion of solids is less compared to liquids and gases. And one more point noticed here, that is generally on heating substances. Generally on heating solids, what happens means you are telling that they expand. They expand. Yes, we are happy by saying that the solids are expand. The expands. What will happen whenever heated? Solids will expand. But there is a phenomena even on heating. Solids contract. Solids contract on heating also. Solids contract. This is a special case. Not all substances, few solids, few substances, they will contract on heating. Few substances contracts on heating, not all. So don't write solids, write few substances. Better write few substances. Few substances contracts on heating. Contracts on heating. Contracts on heating. What are those substances means? There are so many examples. Let us take the standard examples like example cast iron. Cast iron is one type of substance which contracts, and again bismuth. Bismuth also contracts on heating, and we can take Indian rubber. Indian rubber. Indian rubber, and we can also take leather, etc. So these are the few substances. You have to note down the substances. Just a few substances I have noted here. There are, apart from this, some other substances also are there, but generally these are good examples to be noted. There is cast iron, bismuth, Indian rubber, leather. These are the examples for what? Contracts. When heating, whenever we heat, the substances contract. Generally when you do heating, the solids, what they will do? Expands. Generally they will expand only. But there are few substances, like cast iron, bismuth, Indian rubber, leather, they contracts. Okay, no need to worry about these things. These all are different materials. Cast iron one material, bismuth one material, Indian rubber one material, leather one material. These are different materials. Now let us enter into the topic now. So here what happened means, we have to mainly concentrate on expansion of isotropic solids and anisotropic solids. Like that we have some headings. Isotropic, what do you mean by isotropic? Isotropic means expansion in all the directions equally, same way of expanding in all the three dimensions. If you say it is isotropic, that means suppose I have taken one cube. I have taken one beautiful cube here. What do you mean by isotropic? What do you mean by anisotropic? You have to be alert. That means this is x-axis and let me take this as y axis, this is x axis, and this one is y axis, and this one is a z axis, z axis. In all the direction expansion is same. That means how it is expanding along x axis, expansion along y axis, and expansion along z axis, everywhere the same type of expansion is there, equal expansion, all the directions are there, then we call it as isotropic. Isotropic expansion. Isotropic expansion, that means that the solids are said to be isotropic solids. So we call it as isotropic expansion in isotropic solids, means whenever they say isotropic solids expansion, means the expansion of solids in all directions is same. Expansion of solids in all directions is same. So we call it as isotropic. That means uniformly it is expanding, uniformly. This direction, how it is expanding, this direction, in x, y, z, three-dimensional, everywhere, the same way of expansion take place. It is independent on any other factors, then we call it as isotropic expansion. Okay, fine. Leave it about all those things. Just a basic idea you need to have. Now, coming to when we are doing the expansions, we have actually we classify into three categories. Expansions are classified into three categories. What are those three categories? Means first one as linear expansion. Linear expansion. First one is linear expansion. Second one is aerial expansion. Aerial expansion. Expansion. Third one is volume expansion. Third one is volume expansion. By names itself, you have to feel that volume expansion, aerial expansion, linear expansion means easily you can analyze that. Linear means, what do you mean by linear? Lengthwise expansion. Aerial means area wise expansion. Volume expansion means volume wise expansion. That is one dimensional. I can say this is linear means one dimensional. That means only along x axis or only along y axis. That means thin rod. You have to take example as a thin rod. Here aerial expansion means it is two dimensional. Here it is three dimensional. Volume is related to three dimension. So what are these things? Are actually linear expansion. You are telling aerial expansion. That means if you take a thin rod, this is a very thin rod it is. So yeah, then that is we don't consider area of cross section. Area of cross section of the rod. Thin rod means we'll discuss along only length. Along only length. If temperature increases, what will happen? The rod get expands. So now temperature, because of increase of temperature, the length of the rod became as L plus delta L. Length of the rod became as L plus delta L. There is delta L. What is delta, sir? Delta, why you are writing, sir? Delta L means, delta L indicates small increase in length. Delta L indicates small, very, very small increase in length is denoted by delta L. Delta L indicates very small increase in length. Very small increase in length is delta L. Fine. So the length has become little increased because of temperature rise. Suppose let us take here temperature is T degrees centigrade. Here I increased the temperature more than T degrees centigrade. Temperature is increased. It expands. It expands. It expands. Okay, we observe this phenomena. Well done. This is in a linear expansion. Sir, what is aerial expansion, sir? Here also aerial means it is two dimension, means I can take one square plate. This is here I took an example of thin rod. I have taken a small example by taking a thin rod here. Thin rod. Here I am taking an example of what square plate. Simply I am taking here one square plate example. Square plate example. Here example I have taken as thin rod. Here I am taking example as square plate. Square plate. So square plate means it has two dimension. Now what happened means this length is L, this length is also L. Now it expands. It expands. It expands now. So yeah, this is a square plate. This is a square. Let me write again this one clearly. In all the directions, its length has been increased. So here, what happened here? L plus delta L. Here also L plus delta L. That means the length has been increased. Length has been increased in all the directions, x-axis along y-axis. So here the temperature was T degrees centigrade. The temperature T degrees centigrade. Now temperature has been increased. Then T degrees centigrade. So this type of expansion we call it as aerial expansion. Aerial expansion. So here it expanded, and this expansion we call it as aerial expansion. Expansions takes called as aerial expansion. Here the danger is what is the area wise change? Instead of writing here length, okay, length is increased L plus delta L, L plus delta L, fine. So in terms of area I want to write, suppose because it is related to aerial expansion, right? So let me write the initial area as A. Now what will happen to the area? The area becomes A plus delta A. What we wrote previous one also correct. This is length L L. Length became L plus delta L, L plus delta L. That means nothing but initial area if you take A, and now the area is A plus delta A. Area has been increased. Delta A is small increase in area. Increase in area. So delta A like that. So it expands. That is the phenomena we can observe. Aerial expansion. You understood linear expansion. For that we took the help of thin rod. Aerial expansion I took off square plate. Now for volume expansion, what help I have to take? I have to take the help of cube. I will take a help of cube. So cube is there. This is a small cube I have drawn here. So initial volume of the cube, length is L. Let me take L length, and volume is V. Now this cube when temperature is at T degrees centigrade, this is the situation. Temperature here is T degrees centigrade. Now I took the example of cube. Here I took the example for cube I have taken, cube. So initial volume is V, initial volume is V, and here temperature is T degrees centigrade. T degrees centigrade is the temperature. Now when temperature increases, what will happen? All the sides of the cube will increase. All the sides of the cube will increase. Now what happened means here the volume became, now I can write volume became V plus delta V, because your temperature is more than T degrees centigrade, more than T degrees centigrade. So volume increased by delta V, V plus delta V. So linear expansion, aerial expansion, volume expansion. I hope you are clear with these terms, how to handle these situations, linear expansion and volume expansion and aerial expansion, how to handle. I think you are clear now. So this is the information I can provide for linear, aerial and volume basic expressions I have got like that. And to explain linear expansion, we use a term called alpha. Linear expansion. To understand linear expansion, use a term called alpha. What is alpha? What is alpha? Alpha is called as, to explain linear expansion, I took the term alpha. Alpha is called coefficient of linear expansion. Coefficient of linear expansion. Sir, what is this coefficient of linear expansion? Sir, okay, linear expansion means expansion takes place along length. Linear expansion means expansion takes along length. You told, we are happy. But why you wrote coefficient of linear expansion, sir? What does coefficient of linear expansion indicates? Here, coefficient of linear expansion, actually it is defined as, I will tell the first definition. It is the ratio of, it is defined as, the ratio of increase in its, increase in length, the ratio of increase in length of a solid, the ratio of increase in length of a solid per degree rise of temperature, per degree rise of temperature to its initial length, temperature to its initial length, to its initial length, to its initial length is called as what? Coefficient of linear expansion. The coefficient of linear expansion is nothing but, so to explain the linear expansion, what we selected the tool, the coefficient of linear expansion. So to understand linear expansion, I took the term coefficient of linear expansion. What is this term, sir? This term is actually coefficient of linear expansion means it explains the nature of material. Nature of material, what type of material it is there. It is unique for different materials. Iron will have some value, a copper will have different value, and every material will have its unique value to how the whenever heat is given, how the body is expanding, that is the length, temperature increases, how length is changing, how much length is changing from body to body, it is different because of different materials. That nature of expansion is explained by alpha. Nature of expansion is explained by alpha. Let us see here. This alpha is nothing but, here when we are taking formula wise, I can write like this. Alpha is equal to, I can write the formula like that. Alpha is delta L by L, delta L by L into delta theta. This is the formula for alpha. What is delta L, sir? Change in length. What is L, sir? Original length. Delta theta, sir? Temperature difference. Just now we defined here also like that. You observe the definition. The ratio of increase in length of solid per degree rise of temperature to initial length. So here increase of length means delta L. Initial length is L. Delta theta is 1. If delta theta is 1, the definition they told like this, beta. If delta theta is 1, then delta L by L is called as alpha. Then this delta L by L is called as alpha. They defined alpha like that. What is alpha means? It's the ratio of change in length to original length per 1 degrees rise of temperature. Per 1 degree rise of temperature. Like that we can write. Per 1 degree rise of temperature, the ratio of increase in length to original length. So this explains, this alpha is explaining us. First of all, I can also write here now delta L is equal to L alpha delta theta. Delta L is nothing but L alpha delta theta I can write. And what is percentage change in length? They are asking, suppose percentage change in length. How to write percentage change in length? Is nothing but delta L by L into 100. Delta L by L into 100 is called percentage change in length. So from the above expression, if I write like this, see here, observe carefully, this is delta L, this is L. I brought L to the denominator. Delta L by L means actually what we have to write? We have to write like this first. Delta L by L is equal to alpha delta theta, alpha delta theta. From where you wrote this one, sir? From this formula. Delta L by L is equal to L alpha delta theta means delta L by L is equal to alpha delta theta. Now, delta L by L into what I am writing? 100. Alpha delta theta into 100. This is called percentage change in length. What is percentage change in length? Simply I have to write it as delta L by L into 100 is called percentage change in length. So that is also now written as alpha into delta theta into 100. Alpha into delta theta into 100 is called percentage change in length. Percentage change in length. Like that, I can write the formula for percentage change in length. I hope you are clear till here. So here, what are the units for alpha means? We'll see the units and everything in the next page. So here alpha means we know it is coefficient of linear expansion, coefficient of linear expansion. So here, what are its units? Units means, observe carefully here. Delta L, change in length. Length unit, suppose SI meter. Here meter cancels. Only delta theta units only are there for alpha. That is delta theta where it is there, denominator. The denominator is temperature. But here is not simply temperature, temperature difference. Is the formula here is temperature difference. Temperature difference. Delta theta is temperature difference. We know that for temperature difference, centigrade and Kelvin both are same. Temperature centigrade and Kelvin are not same. Degree centigrade and Kelvin are not same. But when you take the temperature difference, delta C and delta K value are same. Because difference in temperatures, either centigrade difference or Kelvin difference is same. Difference in centigrade temperature or Kelvin temperature is same. Here delta theta is difference in temperature. So now what should I write the units means? Here I can write alpha units like this. Centigrade inverse, this is CGS unit. What is centigrade inverse? CGS units. CGS units. And what about SI units? Kelvin inverse. Kelvin inverse is SI units. Kelvin inverse is SI units and centigrade inverse is CGS units. So like that we can take the units for the alpha. Alpha units we can take in this way. Fine. So we got some alpha units and we understood it is. And on heating, material if length increases, that means if expansion takes place. So if solid expands, alpha is positive. If solids expand, alpha value is what should I write? Positive value. Alpha value is positive. So alpha is positive if solid expands. Suppose if solid contracts on heating, solid expands on heating. A solid expands on heating, completely writing on heating we can write here. So here solid expands on, let us write here, solid contracts now, solid contracts on heating. So suppose solid contracts on heating, then what will happen here? What will happen means simply I can write here alpha value as negative, I can write negative. Why sir? When expands, why alpha value is positive? When contracts, why alpha value is negative, sir? Why it is happening like that, sir? Because you observe here. Alpha is change in length by original length. So change means what is change? Change we always write final length minus initial length. If suppose expansion takes place, final length is greater than initial length. Expansion. Final length is greater than initial length is less than final length, it is expansion. If final length is greater than initial means delta L is positive, alpha is positive. Observe carefully here. We told here if solid expands on heating, what? Final length. Expansion means final length is greater than initial length. Final is greater than initial length means delta L positive. Delta L is positive, then in this formula alpha is also positive. Because delta L is positive. Like that we can write. And here you observe carefully. If solid contracts on heating, that means what will happen? Solid contracts on heating means final length is, contracts means length decreases. That means final length is less than initial. So less value minus more value, negative. Delta L negative means alpha is negative. That means we can say alpha value as negative. When we can say alpha value is negative, when solid contracts, length decreases. Solid contracts, length decreases. If length increases, alpha positive. Length decreases, alpha negative. This is a very general phenomena we can analyze. This is a very general phenomena. Next we'll see some more properties about alpha. Here, on what factors alpha depends on? Alpha depends on what factor? Alpha depends on nature of material. Nature of material. Because every material it will have its own way of expansion. Some material expand very fast, some material expand slow. That depends on the material what we selected. So alpha depends on nature of the material what we are taking here. So here next one is its value changes. Alpha value, actually what we wrote, value changes. Its value changes with the unit of temperature. With unit of temperature. With unit of temperature. So you are taking different units, then alpha value change. Okay, centigrade and Kelvin same. I just now I told centigrade difference and Kelvin difference when we are taking, no problem here. But if you take Fahrenheit difference, delta C by 5 is equal to delta F by 9 is equal to delta K by 5. So if you take the Fahrenheit value, difference in Fahrenheit temperature is not equal to difference in centigrade temperature or difference in Kelvin temperature. So difference in centigrade and difference in Kelvin temperature is same. But difference in Fahrenheit temperature is not same as centigrade and Kelvin. So difference in Fahrenheit temperature is equal to what should I write? 9 by 5 of delta C. Or here delta F is also can be written as 9 by 5 of delta K. Delta C, delta K, okay, they are same, but delta F is not same. Similarly, R also delta or Rumor scale if you take, that also changes. Rankine you scale if you take, that also will have different, like that. It changes from where to where? Yes, it changes from with respect to unit of temperature. So the alpha value is not fixed. Alpha value changes with unit of temperature. Unit of temperature. Fine. Now it is independent on what? Independent on length of object. How much length is there? It does not depend on that. It is not depending on length, and it's only because fractional change in by length you are writing, so it does not depend on length. And it does not depend on scale in which length is measured. It is independent. We can write it, this one also independent on scale in which length of object is measured. Like that also we can conclude length of object is measured. So these are the conclusions. So it is independent on length of the object. It is independent on scale which we are measuring the object. What type of scale? It does not depend. It depends only mainly on what? Nature of material, and also its value will be changing with the unit of temperature. So these two factors only alpha depends. You don't, that means if you have taken suppose iron rod, you take 1 meter iron rod, or 2 meter iron rod, or 3 meters iron rod. We call it as iron only, we don't call it as steel. If length is more, we don't call it as steel. Even the 1 meter or 2 meter iron only. So alpha value will be same, and is independent on length and independent on the units what we are taking. If you write 1 meter iron rod, or if you take 100 centimeters iron rod, sir, I changed the units. No, sir. Will the rod alpha value will change? Alpha value does not depend on. Alpha value does not depend on scale in which length of object is measured. You are measuring in meters or centimeters. It does not bother. It does not bother on length of object also. Does not bother on length of object also. It only depends on nature of material. Nature of material. Its value changes with unit of temperature. It does not depend on scale in which length of measured, or independent also we told on length of object. Depends on nature of material. Value changes with unit of temperature. You have to remember this data. So same thing applicable, this type of knowledge we can apply for remaining also. So suppose now I have taken the same information, suppose let me take now beta. Now I am going to introduce a term called beta. Here beta is when we are discussing about aerial expansion. Aerial expansion. So aerial expansion means here what we use the term here, we use beta. Coefficient of aerial expansion. Coefficient of aerial expansion. Aerial expansion or superficial expansion also we can write. Here how it is defined means the ratio of increase in, here aerial no beta, so the ratio of increase in area of a solid per degree rise of temperature to its initial area. Only in the place of length I am changing area beta. So see the definition, previously I wrote linear expansion. Linear I changed as aerial. What I did here? Linear I changed as aerial. Alpha I changed as beta. Alpha I changed as beta. Coefficient of aerial expansion. Coefficient of aerial expansion. So the ratio of increase in area of a solid per degree rise of temperature to its initial area is called as beta. Just wherever length is there, I change it with area. Wherever length is there, I change it with area. And alpha name I changed as beta. Alpha name I changed as beta. Here also I am changing that one, alpha as beta. So beta is now ratio of change in area by original area into delta theta. Delta A means change in area. So now again I have to write here also no beta, delta A by A observed here. Next one is coefficient of, what is the, now we are taking the term beta. It is coefficient of what? Aerial expansion. Coefficient of what? Aerial expansion. And same centigrade inverse Kelvin, even units wise nothing, no problem at all. When solid expands, what will happen? Beta is positive. Solid contracts, what will happen? Beta is negative. Area is increasing. Here area is increasing, beta positive. Area decreasing, beta negative. I hope you are clear with this one also now. Next here also will make change. Here what should I write now? Beta is equal to, that means I have taken beta. At what factors it depends? Let us observe now. Beta depends on what factors means? Same thing beta. Depends on nature of material. Value changes with the unit of temperature. Independent on area of object. Instead of length, we have to replace with area. Independent on area of object. Independent on scale in which area is measured. Area of object is measured. Area of object is measured. So that is the thing what you have to note down regarding beta. I hope you are clear till here beta. So let us see what is beta now. So here beta, what are the points we discussed? aerial expansion, coefficient of aerial expansion, ratio of increase in area of solid per degree rise of temperature to its initial area. So previously when alpha I wrote, here I told linear and here I wrote length here. Now beta I wrote aerial, area. Linear expansion I wrote previously when I wrote alpha, now aerial expansion. That's the only change. Just changes done. Wherever we have to take length, there I replaced with area. Beta is now change in area by original area into temperature. Delta A is A into beta delta theta. Percentage change in area by original area into 100. Percentage change in area into original area into 100 is nothing but beta into delta theta into 100, because delta A by A you take down, beta delta theta into 100. Delta A final area minus initial area, delta A final area minus initial area. Beta, here coefficient of aerial expansion, SI units, CGS units. In solid expansion on heating, beta is positive, solid contracts, beta is negative. Area expands, that means area increases, then beta positive, area decreases, then it is negative. So beta depends on what factor? Nature of material. Every, that means material have its own beta value. Iron has one value, copper has one beta value, like that. So value changes with unit of temperature, independent on area of object, independent on scale in which area of object is measured. Like that we can write here. I hope you are clear with this now. Beta. Okay, sir. Linear we discussed, aerial we discussed. What is next one, sir? Next one is nothing but volume expansion. Volume expansion. Volume expansion, here we use the term gamma. Gamma is nothing but what, beta? Coefficient of volume expansion. Coefficient of volume expansion is called as gamma. Coefficient of volume expansion is gamma. That means now we have to change all the terms in terms of volume. See here, gamma related to volume expansion. So ratio of increase in area you must not write, remove area. And again here also you remove area. And just now what you have to introduce? Volume. The ratio of increase in volume of a solid per degree rise of temperature to its initial volume. Now coming to next, what we are observing? Formula. Here formula, what again? Beta is replaced. A, we just change beta and A. Here what should I write? Gamma. Delta V. Here I have to write V. Everywhere, wherever A is there, I am removing. Beta I am removing. And A place V, and again beta place gamma. Now percentage change in not area. We have to discuss percentage change in volume. What is percentage change in volume is? Yes, it is nothing but change in volume by original volume into 100. What is percentage change in volume? Change by original into 100. Here also let me write like that. Change in volume by original volume into 100. So beta has to be replaced with what? Gamma. And again here A has to be replaced with what? Volume. So I can write delta V is equal to V final minus V initial. So next page, what should I write now? Here gamma again, gamma coefficient of, what should I write now? Volume expansion, coefficient of volume expansion. And here again centigrade inverse, Kelvin inverse, units wise no change. Either alpha, beta or gamma, anywhere units wise there is no change. Units wise there is no change. If solid expands on heating, gamma is positive. Contracts, gamma is negative. Contracts, gamma is negative. Same property beta. What we discussed in alpha and what we discussed in beta, the same thing here also for gamma. So gamma now, what should I write? It depends on nature of material. Yes, correct. And it depends volume changes with unit of temperature. Second point also correct. Third point, independent on volume of object, independent on scale in which volume of object is measured, like that we have to classify all these alpha, beta and gamma. So in this solids chapter, what we discussed, expansion of solids. Solids expand less compared to liquids and gases, we told, because atoms and molecules are closely packed. Solids expands less when heated. So heating, solids expands, and also here what will happen? The solids will contract also. Few substances will contract, not all substances, few substances. For example, cast iron, bismuth, Indian rubber, leather, some etc. We can take like that. These are the few substances contracts on heating. Then we discussed about, after that we discussed about gamma, that is expansion. We discussed in linear, aerial and volume. Linear expansion, aerial expansion and volume expansion. So linear expansion means lengthwise change. Aerial expansion, linear expansion, lengthwise change. Aerial expansion, area wise change. Area means two dimension. That means you have to take plates. Square plate, circular plate, disc. Those all comes under area. Rectangular plate, like that. This is a cube, spheres, three-dimensional things will come under volume expansion, linear expansion, lengthwise change. Aerial expansion, area-wise change. Volume expansion, volume-wise change. So one dimension, two dimension, three dimension. Later individually we discussed previously linear, aerial and volume. I changed those things. So that I hope you are clear with this expansion concept. Expansions of solids introduction is over now.